Okay, so now that we have understood the first law of thermodynamics, let's define some very important variables. Okay, so we know what internal energy is, we know how work is defined, we know how the enthalpy, the Q is defined, the heat, and we know the sign conventions, right? Now just let's define an important quantity or a variable called enthalpy. It's important to understand what enthalpy is because the whole realm of thermochemistry deals with the changes in the enthalpy of chemical processes in different kinds of reactions. So before doing that, before understanding how to use enthalpy in thermochemistry, we have to understand what enthalpy is. Okay, so it is represented by this letter H. Okay, so now let's start with the first law. So we know that the first law is basically del Q minus del W. Okay. Now we know that del W is basically P del V, right? So we can write del Q minus P dV is dE. Okay. Now what we see a very special case of an isobaric process. Okay, we see a very special case of isobaric. So iso means same, and baric comes giving you some kind of intuition about bars. Like, and what is measured in bar? Pressure. So isobaric is a constant pressure process, right? So it is such a process in which the pressure is constant, right? So pressure is not changing. Okay. So now in here, what is happening is we are trying to see what kind of changes occurs in here during an isobaric process. Okay. So dE is basically the change in internal energy, right? So it will become something like E2 minus E1 because dE is a state function. It will only depend upon the final and the initial points. So the difference in the internal energy will just be the difference of the internal energy in the first in the final versus that in the initial. So E2 minus E1, and I'm just calling this as QP because constant pressure. I'm just denoting it that way, and we call this dV. Now dV, that means something like this is going to happen, right? dV, like volume is going to change from V2 to V2 to V1, and we also know that these are also state functions, right? They do not depend upon the processes, the different paths through which they go, right? All right, so now why did we take this process? Like, why the interest in isobaric? Because most of the processes in our environment that generally occur are isobaric processes. So the atmospheric pressure do not change a lot from place to place. Yeah, I mean, if you can go like tens of kilometers, like miles above and below, yeah, they might. But for all practical purposes, the pressure at this point and pressure at this point, it's not very different. So most of the processes that we generally see are isobaric processes, and that is why our interest in this kind of reaction, in this kind of like process, right? So this becomes E2 minus E1. This is del QP. This becomes minus PV2 and plus PV1, right? So let's rearrange this, and I will get this E2 here and bring that PV2 here. So this becomes PV2, right? And I will bring this minus 1, and since I've taken this common here, I get a PV1, and this becomes del QP. So you see how this is getting this form of E2 PV2, and since pressure is constant, the pressure is just a constant. So the E2 plus PV2 minus E1 plus PV1. So there's something going on with this quantity E plus PV, right? So there's something going on with this quantity. So let's this we can write down that E plus PV can be like written down together as, so we can combine these two different parts and we can write them as an H2. So this is basically enthalpy. So enthalpy in this, we defined E plus PV, which was like kind of like getting conserved, like E2 plus PV2 and E1 plus PV1. So this E plus PV quantity we can define for simplicity's sake as another variable called H, and we call that quantity enthalpy. So we can write it like this: H2 minus H1 is equal to delta QP, which is basically the change in enthalpy, right? So the amount of heat exchanged during an isobaric process is essentially the change in enthalpy, is basically enthalpy. So here is the concept that this is the definition of enthalpy, extremely important. During isobaric process, this whole function E plus PV, the function E plus PV is getting a new variable. We are calling it out as, like we got this P del V previously and call it work. Similar way, we are calling E plus PV as enthalpy. So this is the idea of enthalpy, okay? A few points about enthalpy. I'm just quickly going through these because I have dealt this in detail in other videos. If you want, you can just go there and try and understand it better if you want. But in here, the few things that you have to like absolutely understand is this is not an absolute quantity. It's not absolute. What is the meaning of not absolute? It means that you cannot physically calculate the exact amount of enthalpy in any body. Okay, so then why are we trying to define it? Because this variable is becoming important. That's for sure, that this whole thing is becoming important in isobaric processes. That is why the need. But what if it's not absolute? So how is it behaving? So this is behaving like the concept of the potential. You must have learned this in physics, that whenever you have the concept of potential energy, the potential energy of any system cannot be absolutely defined, right? You cannot exactly calculate the amount of potential energy of any body. You will always have to find out the potential energy of that body with reference to something. So you have to get something as a reference point, like the surface of the earth or the surface of this. So if I get this chalk and I put it here, so there is some potential energy involved with this chalk at this position. Now I cannot exactly say what's the potential energy of this body. I can always say what is the potential difference between this body and this and say another body like this. So I can assume this as the reference. I can even assume this as the reference. So related to this surface in here, the potential of the chalk is more than the potential of this space. And relative to the chalk, the potential of this space is less than this chalk, right? So it's always a relative definition. So we have to define a reference point. Okay, so if you cannot do this, we need a reference point, and the reference points of all these are called the elemental reference states, right? Elemental reference states, right? If you want to know more about this, there's a separate lecture. So if you want to know about that, you can go there. But for the purposes of this lecture, please understand that you cannot absolutely get the value of enthalpy of a system. You have to have a reference state, and that is why the elemental reference states are for. So you get that, and you calculate the enthalpy change between a certain process. If you want to calculate the enthalpy change of any reaction, you will always have to refer to this elemental reference states, which is assumed to be 0. You could have assumed anything, but okay, for simplicity's sake, you have to assume some things. All scientists, they came up with this idea of, okay, this is the simplest of all. We get the idea of elemental reference states, like oxygen, what is the elemental reference state of the element oxygen? Is oxygen gas. Because why? Because oxygen is readily available in nature at normal temperature pressure conditions. What is the elemental reference state of hydrogen? It's hydrogen gas. What's the elemental reference state of carbon? It's graphite. Things like that. Why graphite? If you want to know, you can just read more about the elemental reference states. Okay. All right. So similar to the del Q, if del Q is base at constant P is basically the delta H, then a negative del QP will also mean a negative delta H, which means an exothermic process, right? A positive del Q will mean an endothermic. Positive endo in increases energy, right? So del QP, del H, the same thing. Del H is basically QP, like the Q at a constant pressure. Okay. All right. So a similar concept, or is being the next concept that we'll deal in here is the concept of entropy. So we understood what first law is. We understood what enthalpy means. Now we'll try and understand what entropy means. Okay.